Well, hi everyone. I'm Baihan Lin from Columbia University. First, I would like to thank Irina for inviting me to give a talk in this reading group. I understand that it's part discussion and part presentation, and my presentation was around like 30 minutes or so, so feel free to chimp in anytime. I think Kima can also interrupt me or something like that if people wants to have any questions or something like that. Yes. So I will be talking about our projects, A Story of Two Streams, Unified Models of Human Behavioral Agents from Neuropsychiatry. This is a joint work with Gilmore Secchi, Jalil Benifov, Janarinia and from IBM Research, and of course Irina from Mila here. First, as a background, the human decision-making actually was quite different from the traditional reinforcement learning agents. In the traditional reinforcement learning setting, usually for each actions we have at each state for each action there is a cost and reward, and the traditional RL agent will be trying to choose the action that maximize the marginal reward in all future scenarios. Well, in the human decision making, it's more complicated because the reward and cost can come in different aspects, and therefore there might be different attentional weights on different aspects of cost can yield different behaviors. So for instance, a human might be paying more attention to certain rewards and maybe not care too much about certain costs. And also the time scales can be quite different. Some people might be focusing on the present day pleasure, while some might focusing on the long-term benefits. So in short, it is not that simple, and we would like to capture more of this type of reward biases, which actually characterizes the personality or the characters of a human idiosyncrasy. And insights from neuroscience and psychiatry concur with our intuition. In various literatures in neuroscience and psychiatry, we know that the reward system in the brain actually involves different brain regions, which represents the prediction error and values in different in various circuitries and mechanisms, and those interacting systems actually drives different downstream behaviors. For instance, the motivation, approach behavior, or even action selection. And clinical literatures also, many clinical conditions are known to be involved with this type of reward biases. Shown here are a subset of this type of neuropsychiatric conditions, including Parkinson's, addictions, Alzheimer's, chronic pain, as well as the dementia. Shown here is the behavioral variant of the frontotemporal dementia, which is the most well-studied type of dementias in the clinical literature, as well as the well-known ADHD. Our understanding arrives from the perspective of the evolutionary psychiatry, which means that the mental disorders they are actually extreme points in a continuous spectrum of behaviors and traits developed for various purposes during evolution. And somewhat less extreme versions of these traits can actually be beneficial in certain specific environments. So for instance, the fast switching behaviors of the ADHD can actually be life-saving in certain scenarios or environments. And therefore, we arrive at the hypothesis that modeling these disease-related reward biases can potentially lead to better AI systems. So going back to the traditional reinforcement learning problem, the agents takes the action to the environment then reveals the next state as well as the reward feedback to the agent, in which the agent learns through the Bellman equation. In this paper, we are more interested in the reward processing setting. We are given the reward parameters and the environment, and we want to learn the optimal policy for the agent to maximize its future rewards. In the inverse reinforcement learning setting, we are actually given the reward parameters and the agent, and we are trying to infer the reward function in the underlying environment.
Baihan?
Oh, hi.
So we lost you for about maybe 30 seconds. Could you like restart this part? Thank you.
Oh, yes. So, okay. So where did you lost me? Did you lost me from here?
No, we lost your audio from when you went to the RL slide.
Okay, okay, RL slides. Okay, cool. Yes.
Yeah.
But the audio is not good now, right? Yes.
Yes. The video was lost as well at some point, and audio too. Yeah, but it was just the last. This slide.
Okay, cool. Yeah, so I was just introducing the traditional reinforcement learning problem where the agent takes action to the environment while the environment would be revealing the next state and rewards. And in our paper, we are more focusing on the reward processing part, where the reward parameters not only drives the action selection part, but also drives how the agent learns from its interaction with the environment. And in the traditional RL setting, we are given reward parameters and also the reward function in the environment, and we want to infer an optimal policy for the agent to maximize its optimal future rewards. And in the inverse reinforcement learning setting, we are given the reward parameters and the demonstration from the expert or some behavioral trajectories, and we want to infer the underlying reward function of the environment. And in the behavioral modeling setting, where the reward parameters are now unknown, and we might be given the behavior trajectories or and also maybe the reward function in the environment, and we want to infer the reward parameters that can be correspond to, say, a certain neuropsychiatric conditions. And there are 3 levels of reinforcement learning. Everyone knows in the multi-arm bandits, the action was directly mapped towards the reward function, and in the contextual bandit, the state or the context is revealed to the agent such that it can actually infer the reward based on the context. And in the full reinforcement learning problem, the action also consequence and feedback loop into the state, and we can change from state to state. So in this paper, we actually propose a 2-stream RL framework where the reward processing is a split mechanism, follows the split mechanisms where the reward can be having a positive reward or negative reward, and we actually assumes that the representation accounts for the action selection as well as the reward mapping from the context. All has 2 versions, one for the positive stream, one for the negative streams. More specifically, when we are doing the action selection, we take 2 inputs from 2 representations, one positive, one negative, given the state, and try to make our action. And the action, we assume that its consequences give rise to reward also in 2 streams, one in the positive domain, one in the negative domain. More specifically, in the bandit setting, we have this human-based Thompson sampling, which is based off the Thompson sampling algorithm. The main differences from the traditional Thompson sampling is that we introduce 2 sets of parameters. One for the reward history. So if you have a larger lambda, it has a further weights in the past, and if you have a smaller one more towards 0, you would be having more discounts in that aspect. We also have a parameter for the reward perception, which is this W plus or W minus. So it actually tells us how the agent is perceiving current reward. It might amplify the current reward to pay more attention to the current reward, or it can de-emphasize it somewhat. Similarly, we propose the split contextual Thompson sampling based on the traditional linear contextual Thompson sampling, where the parameters for the reward history and reward perception are also introduced in this 2-stream fashion, where we have this because traditionally the reward embedding, the reward mapping is stored in this B and F and nu, and now they are all having this type of reward biases introduced. In the reinforcement learning setting, we introduce based on the traditional Q-learning algorithms, and we introduce the lambda and W in the Bellman's equation. So basically, we introduce two Q tables, one for the positive domain, one for the negative domain, and during the action selection, there are multiple algorithmic choice. In our case, we chose the linear combination of the factors from the Q plus and Q minus. And we through a literature review on different mental disorders, we proposed the following parameters for the reward biases. It's kind of like we're trying to mimic the behaviors or the policies of different mental disorders in this sense. But we also have a disclaimer that we are not arguing that they would be the true data fitted version of those mental disorders, but we think this can somehow simulate similar behaviors as those mental disorders. So for instance,
Baihan,
yes.
I have a question here. So what I understand from your talk till now is that you are not learning these parameters like your lambdas and W's. They are some like fixed quantities, right? These are hard-coded based on your human behavior, right? Like this.
Yeah, so for this very table and very page, indeed, we are not learning the parameters in these steps, but in our ongoing directions, we are now learning those parameters from the real patient data. But it is not just but it is just not presented in this talk yet.
Okay, and I have one more question.
Yes.
Can you also clarify again, like what were your thought process when you divided this into like positive and negative reward? Like, what are the advantages of doing that again?
The reason is because in the neuroscience literature, the brain regions or the neural correlates processing, say, a positive prediction error or negative prediction error are also usually in different brain regions. So they are not necessarily the same system. So that's why we have, and in some case, it is even entirely split. So basically, the first represents those, say, positive prediction error and negative prediction error separately, and later on integrate them together. Yes.
If I could add one more thing, there are also lots of literature, like in psychiatry, this famous paper by Carrot or by Stick, by Michael Frank and others. And anyway, so the point is that in different kind of conditions or disorders, there is a clear imbalance in processing positive and negative reward, as well as imbalance in kind of memory of positive, negative reward. Example, like patients with Parkinson's disease, not on medications, they seem to learn much better from negative reward than from positive. But when you give them particular medications like L-Dopa and so on, which kind of raises a level of dopamine, they vice versa. They start gambling. They start going for positive reward and completely disregarding negative. So there are these kind of observations from patients. There are kind of anatomical observations about the two-stream reward processing. And what we kind of just tried to summarize was these four different aspects, how much people with different kind of reward processing biases, how much they, in a sense, pay attention to positive or negative reward now, as well as positive and negative reward memory. Because like ADHD, addiction, Alzheimer, chronic pain, all those conditions, they have these imbalances in a sense. And with Parkinson, it was like one clear example where reward processing is quite biased. That is why, again, the disclaimer is by no means we claim to have like captured the full picture of disorders. It was kind of just used for inspiration here. But it was an attempt to capture well observed in a bunch of literature biases towards positive or negative, and as well how much you remember positive and negative rewards from the past. Yeah, so it's mainly that. And as to the question about the parameters, yeah, right now, and many experiments, they were just set as an example, just to show what the kind of flexibility in those parameters could give you. But as Baihan mentioned, now we're actually working on trying to optimize them and adapt them to data, because they are very important hyperparameters, obviously. Okay, I'll let Baihan continue.
Yeah. Thanks, Irina, and thanks for the question, Kima. Yeah, so that's basically the intuition why we have the speak mechanisms in the first place. And Irina also gave a very good introduction of certain mental disorders and why we chose those imbalanced reward biases this way from this table. I'll go to the next page. So as a proof of concept, we actually first show that in say the UCL classification task, a certain mental variant can actually be beneficial over and beats the baseline, which is the Thompson sampling in this case in the Bandit setting. So for instance, here in 4 dataset of the UCI dataset, we have different mental variants. And we also, by the way, the M, I didn't mention that earlier. So M, the moderate, was supposed to model similar to healthy human subjects, because in our daily life, we're not going to remember the past for 100% of time. So we have a moderate amount which is balanced in the positive and negative domain, but actually forgets 50% of the history. So basically, it's kind of like in our daily life, we do forget sometimes. And shown here, the positive reward environment would be that you are only learning from the successful prediction that you made. And the negative reward will be you only learn from the failures that you make. A normal reward would be the traditional way that you learn from both the correct prediction and the wrong prediction. And we show that in three different environments in 4 data sets, different mental variants of our a split version of the Bandit algorithms actually performs better than the baseline Thompson sampling. And then we also have synthetic task as a sanity check for not so Gaussian reward distribution. The easy way would be the Markov, the multi-arm bandit, where you can choose from certain arm, and it can draw from a distribution which is not necessarily Gaussian. Or you can have a more complicated version of the Markov decision process, where in the first state, for first action, taking left or right gives you 0 reward, but the next one would give you certain type of reward distribution. So in this case, you will have to have a state representation to meaningfully learn from them. So here is one of the examples. Shown here is one of the weird reward distribution, which are both by model. The orange reward distribution is clearly the better arm, since it has a better means, which is shown by this dashed line. And the blue ones will be more towards the left, meaning that it's more negative. And we show that here, the red curve and the green curves are 2 numerical implementation of our split queue learning algorithms. And it actually converges to the better action, which is the middle plot. Meaning the better action is taking the right curve, the right arm, choosing the orange reward distribution, and also it has a better cumulative final rewards in the long term as well. It is beating other benchmark, for instance, SARSAR or double Q learning and Q learning, as well as another variant of this 2-stream processing benchmark, which is called Max Payne. And here it gives us more details about how the Q values give the Q tables for the 2 actions changes over time. So the first 2 on the left correspond to the positive domain, and the second 2 on the right correspond to the negative domain. But it doesn't have to, because in the double Q learning there is no positive and negative. but it shows that our Q learning, our speak Q framework offers a smoother transition for those learned parameters, and it doesn't necessarily follow the exponential learning like the other ones. And we also explored on the IO gambling task, which is a very popular psychological experiment where many people have conducted experiments on the patient as well as human subjects. We see that the reward distribution in this red square is very weird. It is highly non-Gaussian, and also the two schemes that we are comparing, the scheme 1 and scheme 2, also has a very different reward distribution from traditional RL tasks. So the task is to choose from 4 different DACs, A, B, C, D. A and B are supposed to be bad DACs because they have an expected value of -25, while the C and D is supposed to be good DACs with an expected value of +25. They always have a win, a set number of wins, where A and B's are positive 100, while C and D's are positive 500, but they can have a loss or the negative reward in different frequencies, which was listed here. Sometimes it can be very frequent or infrequent in a sense that it actually infrequently have a large amount of negative reward, or frequently with smaller amounts.
Baihan,
yes.
I just thought maybe I don't know how many people actually familiar with Iowa gambling task. Maybe you could just give a little bit of a explanation. It's
okay,
classical thing. It's like a plain vanilla classical thing, maybe in psychology, but just a little bit of background about the task.
Yes. So, for instance, in the scheme 1, which is the first block on the table, if you chose from deck A, you would receive a positive reward of +100, but you receive a negative reward in a stochastic fashion, where you have 10% of chance to receive -150, 10% to receive -200, 10% to receive -250, 10% to receive -300, and also 1% of -350. So that's this P means. P means the probability of receiving this amount of negative reward. So is it clear to anyone, or should I elaborate more in more details?
Yeah, perhaps you can just go ahead. I mean, but if people have questions about Iowa gambling task, we also can get back to it at the end. But doesn't sound like anyone had questions in the chat room or. Okay.
That's good. Yes. So here, if we pay attention to the percentage of choosing the beta DACs, we see that the short-term dynamics actually offers very interesting behavior trajectories, which matches the clinical understanding. So for instance, if we pay attention to the black curve, the black curve is addiction. So we see that in the first 100 rounds, the addiction actually converges the fastest to the beta DACs. However, later on, it seems to be doing very poor. So it was not only caught up by everyone else in the last 10 episodes towards 500 rounds. It is the second to the last. So that matches our clinical understanding, because the addiction patient, it pays less attention towards the negative rewards. And it forgets about the negative experiences in a very much. So that's why at first it actually learns about it might learn about the frequencies of the positive ones, but later on it decides to converge to a policy which more leaning towards the positive rewards instead of the negative ones, because it forgets most of the negative the information from the negative stream. And also here, if we do a t-SNE, it somehow shows some sort of clustering for different types of reward biases, but not too much. And we also find some universality of this type of mental variants. So similarly, here shown here is the split models in the bandit setting, contextual bandit setting, and RL setting. Now the blue curve is the addiction. You see these similar behaviors as well. So in the short term, it converges quickly, and later on it got caught up. So we also perform we also tested different mental variant as well as our algorithms in the PacMan game in a non-stationary setting. So for the positive and negative reward streams, we can have reward muting, reward scaling, and reward flipping. Reward muting means that for each round or for each n rounds, you can turn off, you can mute one stream, zero stream, or both streams. So for instance, if the positive stream is muted, it means that when you eat a dot, you receive no scores. You receive no reward. And we can also have reward scaling, meaning that if, for instance, if the negative reward is scaled up, it means that it is timed 100 times. So if you got eaten, you would have 100 times the original punishment that you would get. The reward flipping, similarly, you can flip one, both, or neither of the stream, where in this case, if you eat a dot, instead of having a plus 10 points, you might have a negative 10 points. And if the negative stream is flipped, if you are being eaten, you are rewarded, say, 500 scores. So we change this every n rounds to simulate some sort of lifelong learning setting, so that you are constant within certain batches of games, but you are changed over time. So in our evaluation, shown here is the RL setting. We see that the split Q learning is consistently very competitive from the traditional Q learning algorithms in all of the non-stationary scenarios, and even beating the Q learning in certain reward scaling and reward muting scenarios. And more interestingly, we also show that the reward flipping in the reward flipping scenarios, some mental variant, for instance, the ADHD and also dementia, due to ADHD's fast switching behaviors, it actually adapts to the reward flipping very well. And it receives the overall positive scores, despite the fact that the reward flipping is happening, say, every 1 game or every 10 games. Much better than the baselines. And similarly, we also run different contextual bandit algorithms also in this game. Despite the fact that the contextual bandit is not supposed to play games, but we also see a similar effect here, where some mental variants, say the ADHD and also the dementia, is performing much better than the traditional algorithms like contextual Thompson sampling, linear UCB, and EXP4. And here, I'm not sure how my internet is holding up, because it seems to be moving extremely slow. But anyway, later on, if you see this GIF either on the Git repositories or the videos, you will see, for instance, ADD accounts for the addiction. It usually takes very risky behaviors. So it only chases the reward. It doesn't care about whether or not it got killed or not. So it can chases the reward even if it follows a ghost in dangerously close proximity. And if you look at the CP, which is the chronic pain, you see that it doesn't really cares about the positive domain anymore. So it doesn't really cares about how many dots it is. It only moves when an imminent threat is coming. Say a ghost is nearby, then it actually escapes. So it can have very, very high negative domain, the negative scores, because it keeps hiding and never pursues reward, which matches the clinical studies where it's actually focusing more on the negative. It has a very high bump in the negative stream during the learning process. My computer is stuck. Okay, great. Yeah, so we also tested this in the multi-agent setting, in the iterative prisoner's dilemma. So in the prisoner's dilemma, in the classical way, we have two agents, the two prisoners, and they are being interrogated. So if both of them cooperate, meaning that they actually stay silent and don't talk to the policeman, they will both serve 1 year. And if they both talk, they both defects to each other, they both serve 2 years. However, if one betrays the others while the others actually cooperates, then the betrayer actually goes free, while the one that is being betrayed will be served 3 years. So representing it in the matrix scheme, we can have two actions for each agent, cooperate or defect, and it can receive either a reward or temptation, penalty or succor. And the reward payoff has the temptations will be the biggest from all, followed by reward, then penalty, then succor. So is the setting clear to everyone? Okay. So the iterative version means that you play this game for multiple times, and in the psychology and clinical literature, people usually recruit patients or human subjects to play this game for multiple times, and they record the trajectories of how they behave when interacting with the other human subjects across time. So maybe one decides to cooperate in the start, and later on, because it is being betrayed for several times, it might become more defective, or vice versa, or something like that. So it is a dynamical process. We are interested in this setting to explore how do different attention bias shape behavior. The reason is because the 3 levels of the reinforcement learning, the bandit, it doesn't care about anything about the context. It has no attention on the context whatsoever. The contextual bandit, it pays attention to the current context, while the reinforcement learning agent is focusing on the context, multiple contexts in multiple states. So it compares different contexts and yields different weights on different contexts. So does the attending to the context for an online learning algorithm help to mimic human behaviors or not? And we also want to see which of the 3 levels of the two-stream RL offers the richest insights. So we have run these tournaments with 2 and n agent setting. So we compare this following bandit algorithm: Thompson sampling, UCB1, epsilon greedy, EXP3, and also the human-based Thompson sampling. For the contextual bandits, we have contextual Thompson sampling, linear UCB, EXP4, and the split contextual Thompson sampling. In the reinforcement learning, we have the model-based and model-free contestors, the Q-learning, double Q-learning, and SARSA, as well as the split Q-learning. We also have 3 handcrafted agents, which is usually used in AI, the prisoner's dilemma tournament. One is to tit for tat, which is a popular AI algorithm. If you betray me in the last time, then I will betray you this time. If you cooperate last time, I will cooperate this time. And we also have two agents which always defect or always cooperates. And we have mental variants of the two-stream unified models in 3 levels. First, in different algorithms, we have this. Oh, by the way, when I'm in n agent tournament, it is similar to the 2-agent tournament, except for the fact that if one or more betrays and one or more cooperates, then the cooperator receives a reward of succor, while the defector receives the temptations. So otherwise, it is similar to the 2-agents case. So this heat map shows the success rate, meaning that it's the cumulative normalized reward over different rounds, and also the teamwork, meaning that the collected reward by these pairs of playing games. And first we can, if we actually take the average by different pools of the agent, we see this dynamics where the cumulative normalized reward, the RL has the highest cumulative reward, followed by the handcrafted version, followed by the multi-arm bandit, and then the contextual bandit. In the 3 agent scenarios, where we have an contester from the bandit pool versus the contester from the contextual bandit pool versus the contester from the RL pool, we see that still the RL has a higher score than the bandit, than the contextual bandit. We hypothesize that the reason why the reinforcement learning is good, it indicates that the optimal policy should hold memory for different state representation and allocate attention to different contexts across the states. It also indicates that in zero-sum game, like the iterative prisoner's dilemma, the learning system usually involves multiple stages of the context. And we also hypothesize that reason why contextual bandit is the worst is because the attention to the current context is not sufficient, because the learning system might mix the context-dependent reward mappings of multiple states. And we see that the multi-arm bandit, it performs relatively well just due to the fact that it ignores the context entirely. Therefore, there is no interfering effect of such. If we compare the cooperation rates, meaning that the percentage of cooperation across time, and we can also have a competition heat map, meaning that it is the relative reward, the reward of the current agent versus its opponent's agent, minus its opponent's reward. And we can see dynamics which looks like this plot. Shown here is the percentage of cooperation over the entire iterative games, over 50 rounds. So you can see that the contextual bandit is the most cooperated one of the 3 RL pools, followed by the reinforcement learning, then followed by the bandits. Similar things happens in the 3 agent scenarios. So first thing that we notice is that the betrayal is not necessarily the best policy. So in many behavioral literature, and also the traditional AI literature, most agents learns to betray in the end, because the betrayal seems to be something that most agents, most strategies converges to. But it indicates that betrayal is not necessarily the best policy. So the RL learns to adapt across the different rounds based on its opponent's action. And despite both good, unlike RL, the bandits' learned policy will oversimplify, so it doesn't have the flexibility to account for major change in the state. And if we compare to the mental variants in these different scenarios, we see more diverse behavioral trajectories. And it seems to me, from the first look, it doesn't seem to have too much universality. So it means that there are more subtleties in these split mechanisms in these 3 levels of agents. So in the multi-agent setting, at least in the iterative prisoner's dilemma, the distinguishment of the 3 levels of RL seems to be more distinct than the reward biases itself. And if we pay attention to the cooperation dynamics on the right, we also see that the bandit algorithm seems to be all learning somehow a decaying reward cooperation rates, while the contextual bandits seems to be converging towards somewhat more or less a random policies. So sometimes it doesn't learn very well, while in the RL level, the trajectory seems to be much more interesting. So you see that some agents seems to be more defective from the start, but later on learns that maybe the cooperation is a better option, and later on seems to be then converging towards a more defective state. So shown here, each trajectory is one agent trajectory playing with another agent. The color doesn't indicate anything. So all those cooperation behaviors matches multiple clinical studies in the dementia, ADHD, and addiction. More discussion in the archive version. And finally, we perform some sort of behavioral cloning with the demonstration reward. So the difference between this behavioral cloning with the traditional RL is that, for instance, when you receive a state and you want to make an action, but when you make an action, you do not receive the reward from the environment anymore. Instead, this reward comes from the fact that whether or not your chosen reward matches the real behavioral data. So for instance, if you are playing, do you have any questions? Okay, yes. So from this data set of 160,000 individual decisions from 8 behavioral literature, we curated 8,000 behavior trajectories of 9 actions, which we split 8,000 to be the training set and 257 as the test set. And shown on the left is the heat map for the percentage of cooperation for the 257 test case. And on the right is the average ones over the test case across time. So 0 to 8 is the 9 actions. So from the 0 is the first action. So the first thing that we notice is that the human data is the black curve. Its cooperation by the real human data tends to decline slowly from around 70% to around 40%. And the RL algorithm, you cannot see it because they are all 0, all seems to learn to defect at all costs after training on 8,000 training data. While the contextual bandit seems to be converging to a fixed cooperation rate somehow. The bandit algorithm learns a more diverse cooperation rate across test sets, and also the in which the UCB1 and epsilon greedy both capture the decaying property, mimicking the strategies of the human action. And this is matches. So this intuition was matched by the prediction error analysis. So shown here is the prediction error. So the 0 is white, and positive meaning that you overestimate its cooperation rates. Red means that you underestimate the cooperation rate, and this is the prediction error. And we show that the multi-arm bandit in general, especially the UCB1 and epsilon greedy, appear to be the best capturing the human cooperation behaviors across time in the data set that we curated. Okay, so that summarizes the results. So ongoing direction, of course, in the AI reward alignment, we are interested in seeing what would be the optimal reward biases, for instance, for longest survival time, highest final scores, or something like that. We are also interested in exploring more in the multi-agent domain, and we are also doing clinical modeling on actual patient data. We want to learn the parametric reward biases. And finally, we also want to explore how it would work in the deep Q networks. In conclusion, we propose this two-stream framework of behavioral agents to model the human decision-making process in online learning, reinforcement learning, and multi-agent interaction. We show in machine learning aspect that it is simple yet powerful and more adaptive to the traditional RL problems. And in the neuroscience, this is also the first attempt at general to unify the model of reward processing and disruption across a wide population, including both the healthy subjects and mental disorders, which we find quite useful potentially for neuroscientists and psychiatric to draw new biological insights for those disorders. And thank you, everyone. And do you have any questions? And feel free to contact us for more questions and collaborations.
Hi, I had a question, Baihan.
Hi.
Thank you for the talk. Going back, maybe this is more like a high-level question about the mental disorders work. So as far as understood from the talk, you were providing this sort of general framework for the sort of model-free kind of approach, right? You this sort
Yes.
of Q learning TD-based framework. And I was wondering, so are you suggesting that these clinical disorders are mostly in reward bias rather than sort of world model bias? You could imagine there being also an issue coming from misspecification of the world model that the diseased mental states are using.
Yeah, I think it's a very good question. So the question is that, so for instance, why do we choose this subset of psychiatric disorders, and whether or not we are oversimplifying those mental disorders with just the reward processing aspect of them, right? So my understanding is that indeed there are more towards those mental disorders than merely the reward biases itself. But for instance, in this paper, we chose 6 of them. We are planning to extend more because those 6 of them has clear clinical indications for its relationship for 4 different reward biases. So basically, those are the disorders that has been shown to be directly correlating to say the dopaminogenic modulations during the learning process or the deployment process or something like that, and we're not covering other ones because those ones are not as clear in the clinical literature. So for instance, autism obviously is another disorders that we're interested in, but since autism spectrum disorders, it has far more complicated variables inside that we feel uncomfortable to model at this stage. So we're not choosing it as our subset of the neuropsychiatric conditions. But we chose these 6 of them because those are the ones that we find has already shown to be directly correlating with those type of modulation.
If I can add something, I think, Max, back to your question, I think the question was more whether there are other aspects of those disorders that we do not model that go beyond just reward biases. And of course, yes. And as I mentioned again, I mean, the disclaimer in the beginning was that we use the name of those disorders just to inspire particular biases in reward. So do not really take it as a serious model of psychiatric disorders, not yet. And of course, we just really kind of scratched the surface and picked on one particular type of a bias from the literature, positive, negative reward kind of processing bias. We didn't really even try to model kind of some disruptions in the models of the world associated with those disorders. That's why it was more on the side of, if you use intuitions from psychiatric literature about a bit more richer and flexible ways of kind of processing reward, and you just use a quite simplified way of capturing it in reinforcement learning and Bandit algorithms using these 4 parameters. So you kind of get a bit more flexible algorithms that seem to, well, in general, work better because they're more flexible. That's all. So it's by no means we claim that we really captured the spectrum of disorders with a good kind of neuroscientific reward processing model. So that would be very interesting, but that's kind of a long and kind of future project. So that's why, Max, you're absolutely right. I mean, there are quite a few things we didn't even come close to capturing.
Oh, it's still very interesting. Thanks for the answers.
Yeah, so it's really scratching the surface. Like you read the literature, you see that there are these clear positivity, negativity biases, as I mentioned in Parkinson, like that example, and vice versa in ADHD, and vice versa in addiction, and then again chronic pain, and then schizophrenia. And what you do, you just get these intuitions into quite a trivial extension of Q-learning or contextual bandit algorithm. Just add the hyperparameters. And even with this extra flexibility, they seem to adapt better to kind of wider variety of environments. And so just So that's kind of 2 cents from neuroscience and psychiatry towards AI. But it would be really great to, if we continue working on that, and if people are interested at Mila, there are many interesting things that can be done here to really capture much better reward processing in general and at the fringes of the distribution in terms of particular disorders and so on. I think it's really exciting direction.
Yeah, and I would like to also elaborate briefly on other ongoing directions that we are modeling beyond, say, the reward biases. So one of the things that we're currently modeling is, for instance, attention mechanisms, because we know that when those many disorders, so for instance, ADHD, of course, it actually has its fast-reaching behavior, not only for the reward processing, but also how it actually accumulates for those attentional weights. So for instance, we in the reinforcement learning problem, that will mean that when we have different features, and sometimes those features can also be in different dimensions, usually we would assign different attentional weights on those aspects. And in that sense, we can also model the attention with different parameters. For instance, how quickly those attention would change over time, how they will shift over time or drift over time, or for instance, how much memory that we want to hold, even for the attention weights that we impose on those features. So that's another thing that we are currently modeling as well.
Can you hear me?
Yes. Yes.
Oh, finally. I think was Max who asked the question. Going back to that one, I think is really interesting, and I don't have a reply to that, but I have some comment. And the comment is that so many of these conditions, I'm much more familiar with schizophrenia, also have a very significant effect on perception, right? So there are real clear perceptual differences that may go along the lines of what Max was suggesting, but there is some consensus that they all may be related to behavioral differences, right? Because part of the motivation of this work is precisely the idea that perception and action cannot be completely disentangled in the brain or in the mind, right? So that if you have perceptual differences, is because there are action, motor control differences that are affecting how you perceive. So this, in a way, is an approach to get to, as Irina was saying, a more complicated model. But if we can explain many of the differences in behavior that we see with the simple model, that would lend some support to the idea that even those perceptual differences can be explained by just differences in behavior that are essentially driven by decision making.
Are there any other questions? I know there was a lot of material in this talk, which was condensed into a short presentation.
Thanks, Baihan. It was a nice talk. Thank you.
Thank you, Kima. Thank you, everyone.
Any questions? Look like you're more than welcome to contact us after the talk. As I said, the talk was trying to cover several papers in 50 minutes, and there are various settings and kind of particular algorithms and so on. But if anyone is interested, we're more than happy to discuss.